Hey, so this is Joe, and this is the first part of the third chapter of Stewart's calculus, and we're going to be talking about extrema and critical values. So extrema, these are the four kinds of extrema that we can have. We can have absolute maxima, absolute minima, local maxima, and local minima. So an absolute maximum value on a function is a value of that function on its domain D at some value of xc, such that f of c is greater than or equal to f of x for all values of x. So really, what this is saying is it's the greatest value on that function in a given domain. The absolute minimum is the same thing, however, it's such that all values of f of c are less than or equal to f of x for all x's in the domain D. So really an absolute minimum is just the lowest value of f on a certain function for all the values in its domain. And now local maximum and local minimum are a little trickier to define in words, but they make a lot of sense when you look at them on a graph, which we're just about to do. So a local maximum is a value of f on a given domain D at a value c, but it's when f of c is greater than or equal to f of x, but that x is only the x values near c. And so that near can be a kind of elastic term, and I'll show you what I mean by near, and I think you'll just get a kind of conceptual idea about what that is when we look at a graph. And a local minimum is the same deal, but when f of c is less than or equal to f of x. So let's go over here and look at a graph and kind of figure out what all of these things are. Alright, so here we go. We've got this kind of nonsense or piecewise function that it doesn't really matter what the equation is, but so absolute maximum. This cusp point right here is the highest value of y for all of the values of x defined. So we're going to write that in. It's an absolute max. And now the absolute minima can be endpoints of the function, so can absolute maximum. And the absolute minimum is this one. This is the lowest value. It's that endpoint right there. That's the lowest value on this whole function for this domain of x such that it's between a and q, presumably inclusive. So that's the absolute minimum. Now, because the definition of a relative or local maximum and minimum states just when x is near, that c, that what we're going to call a critical value, and I'll define that later on, we can have multiple of these local extrema in a function. So this is a local maximum right there at the top of that curve. It's not the tallest value in the function, but for all the values near it between a and c, that's the highest value. So that's a local maximum. And this also is a local minimum. Between all the values, b to p, that's the lowest value. So but this cusp point right there, that's also a local max. And now the range of x over which or I should say the domain of x over which it's the biggest value, is smaller than the domain over which this local minimum is the smallest value. But we still call it a local max because there are a ton of points that it's greater than, and the function's increasing here, the function's decreasing there. This also is another local min. And now this point right here is neither a local maximum nor a local minimum. And I'll show you why later. We're going to actually call this thing a point of inflection. It's when, but I'll define that later. And this endpoint is nothing. That's neither a local max nor a local min, because we can't have relative extrema at endpoints. So you may be wondering, how does calculus kind of factor into dealing with extrema? And it's very important when we're talking about extrema, and extrema are very important to calculus because at the base of it all, Fermats Theorem. And the theorem says if a function x has some local extrema at a value of xc, and f of c exists, then f prime of c is 0. So that means the derivative is 0 at any local extrema. And now you might be curious about the stipulation, well, if f of c exists. Well, And you might say, well, are there any local extrema where f of c doesn't exist? And yes, but most importantly, there are extrema where f prime of c doesn't exist, and that's at cusp points. And we can still have local extrema at cusp points, but we're going to need to do a different kind of analysis to figure those out later on. Or yeah, actually, right about now, because now we can define what a critical point is. A critical point is a number of c, at c such that f prime of c equals 0 or f prime of c doesn't exist. And so a critical point, there is most often going to be some sort of extrema there. Actually, pretty much all the time there's going to be extrema there if we look at Fermat's theorem. And the point where the derivative doesn't exist, well, sometimes that's not an extrema. Sometimes that's a discontinuity, or sometimes, yeah, a discontinuity. But if it's a cusp point, then it is an extrema. So just bear that in mind. If the derivative at a point is 0, then it's a local extrema. If it doesn't exist, then it's either a cusp point, in which case it's an extrema, or it's a discontinuity. And so let's look at that graphically. Here we go. So let me just demonstrate that Fermat's theorem kind of works. At all these local extrema that we called local extrema, we've got the derivative is 0. Well, except for the cusp points. Yeah, and there we go. Those are the cusp points. And now, this guy, the derivative is 0, but there's something else going on. It's not really an extrema, because the values keep going up here, the values keep going down here. It's not the highest nearest value. And why is that? Why is there that exception to Fermat's theorem? So by the way, all of these, including the cusp points, are critical values, and as it turns out, local extrema, except for point P right there. And why is that? Well, as we'll see, if you take the second derivative of the function, so f prime prime of P, you would get 0. And so this is called a point of inflection. Let me write that down. And that's where the second derivative is 0, and the first derivative can be 0 as well. And now we can start talking about concavity, since we're bringing up this second derivative. And this is why in concavity you need to use it to prove, when you're analyzing a function algebraically, whether a function or a critical point is a maximum or a minimum or neither. Alright, so we're going to use the second derivative to get an analysis much in the same way that we use the first derivative to tell us something about functions. So we know that if the first derivative of a function is greater than 0, then that function is increasing. We know that if it's less than 0, it's decreasing. And that's just because of the slope. If you have a line with a positive slope, the line's going up. If it's a line with a negative slope, the values are all going down. So let's get something similar for that for the second derivative. Alright, so let's get something similar for the second derivative. Alright, so we have, if the way it goes is if the second derivative is greater than 0, it's concave up. Just remember the up is associated with the greater than. If it's concave down, if the second derivative is less than 0. And you've got an inflection point if the second derivative is equal to 0. So, what does concave up and concave down mean? Well, here's how you can think of them. Concave up is when the function is greater or is above all of its tangent points. Concave down is when the function is below all its tangent points. You can also think of them if concave up, if you put your hand in the same curvature and poured water into it, you'd be able to hold water. Concave down, if you made your hand the same curvature of the curve and poured water onto it, it wouldn't go into your hand. But let's look at that actually on the graph. Alright, so we're going to look at some concavity for this, again, this function here. So, between a and b, if we draw all the tangent lines out, the function ends up lying underneath them. So we know that that is concave down. And also, if you were to pour water on the top of that function, if you can imagine that, the water wouldn't go inside the function, it would run off the top. So that's concave down. And also, if we think about it in terms of rate of change, so the rate of change of this function goes from positive increasing to negative decreasing around the relative maximum. However, the values those rates of change, these slopes, are getting are changing with a negative value. They're all in the process of getting smaller. It's kind of, if you imagine throwing a ball up, gravity is acceleration, that's the second derivative, and gravity is always negative. So that ball is always going to want to come down. So that's concave down. Now, we have a point, we pass through B, which is a point of inflection where it changes from concave up to concave down, where the second derivative is presumably 0. Or sorry, from concave down to concave up. And so between B and C, the function is concave up. And we can see that we put the tangent lines, the function lays above the tangent lines. Also, it could hold some water. And so here's a cusp point, and that's because the function is abruptly changing from concave down to concave up, but the function is going from increasing to then decreasing. And that's why there's a cusp point there. And then here, P, there's a point of inflection because, and that point of inflection is also a place where the derivative will equal 0. And it's because this is a special case where the function's changing from concave up to concave down, but it's decreasing the entire time. And so the point of inflection will end up looking something like that. Alright, so now we're going to do a practice problem, and these are pretty common problems, and they'll come in handy for a lot of different applications. But what we're going to have to do is we have a function f of x, and algebraically, we're going to have to find the extrema of it. And we're not told what these extrema will be. We have to figure that out for ourselves. And after we do the problem, I'll show it to you. I'll show you the graph of this function, and you'll be able to pretty easily see where the extrema are. And on the AP, since you're not going to have your calculator the whole time, you're not always going to get to graph the function because it's not always going to be a function that you'll be able to graph all the time. So you have to be comfortable with doing this algebraic analysis of it. Okay, so first we've got Fermat's theorem that says that at every point that the derivative is equal to 0, you're going to have some sort of extrema there. Most of the time, unless it's that special point of inflection case. And so we're going to find those critical points. And also we're going to have to find any points at which the derivative doesn't exist. But because this is a polynomial, we know that the derivative is going to exist for all points. So we're really just looking for a point at which the derivative is 0. So let's take the derivative of f of x. So we've got f prime of x is going to be equal to 1/3 minus x. So let's set that function equal to 0, and we will get 1/3 equals x. So the derivative is 0 at x equals 1/3, so we know that that is a critical point. But we don't know what kind of critical point it is. And this is where using the second derivative in concavity is important, because every time, write this down for you, when we have a function that's concave down and there's an extrema in the portion of the function that's concave down, then that extrema is going to be a maximum. And if it's up, it's going to be a minimum. So that's why using the second derivative is really important. So now we're going to do that test on this function here. So we're going to take the second derivative of the function, which remember is just the derivative of the derivative. So we've got f prime prime of x is going to be equal to -1. So this means that the function is always going to be concave down because f of x is less than 1. So since it's always concave down, then that means that this critical point is going to be a maximum. So or a local at least a local maximum. It could be a relative maximum. So we know that we have f of 1/3 is going to be, and I'm going to leave a little blank here, some kind of. So we know that if there's no other value on the function that's greater than this, than the value at f of 1/3, we know that that's an absolute maximum, otherwise it's a relative maximum. And since we're not given any endpoints here, we wouldn't be able to find any absolute extrema. So let's find what well, actually, if we do just look at this function for a second, we see it's a parabola because it's a polynomial to the second degree, and we see that it's negative, so it's a downward-facing parabola. So the maximum point is going to be the absolute maximum. And if you can't visualize this in your head, then we can look at the graph so you can get kind of a better idea of this. But that's kind of what you have to do to test whether it's a absolute or relative maximum, or plug in values for f and see if they're bigger than, or plug in values for x into f and see whether they're bigger than this maximum point. Or do more second derivative tests to figure it out. But let's go over here and look at the graph of this function. Alright, here we go. We've got x equals 1/3 at about there. And here's a maximum value. The whole function is concave down, and there's no value that's greater than it. So that is, in fact, an absolute maximum. Now, if, say, this function were to have been different and curved around and gone up like that, then this would just be a relative maximum. But we could have figured that out if we had plugged in super duper small values for x, and we would have eventually got a value that was greater than the value at x equals 1/3. So that was Extrema, and stay tuned for the next videos because chapter 3 is pretty interesting.